So hi everyone, welcome again to CSE 564, Visualization and Visual Analytics. And today we're going to be talking about visualizing volumetric data. So it goes right here. So we talked about last time about volume data generation. Here's one more slide on this. So basically we take these data sets you acquire by X-ray CT or scientific simulation, and essentially they would reproduce these slices, and these slices then get stacked and become a three-dimensional volume, like sampled on a grid. So this is like basically one of those sets of slices of a human head, where you can see the top and the across and to the bottom. And so these slices are stacked and then put into volume. And now we're gonna three-dimensional render this volume, okay? So the way we do this is basically we either try to see an aneurysm, which is right here. Maybe you see a skull fracture. Someone got beaten up in a bar or something like this. You know, broken jaw. Then here you can see carotid arteries, you know, also volume rendered again. All these are really acquired data with CT scans and then put together as a shaded object. Okay, so you can actually see three-dimensional geometry and structure in that, you know. So you can tell me what you like better, three-dimensional object or this kind of slice representation, okay? Same thing, okay? Just now this is volume rendered. So hopefully you're curious enough to figure out how this actually works. How can you actually volume render or graphically represent these slices? Okay, so, you know, the wait is over. I'm gonna tell you this now. So basically you're going to use a process called ray casting, okay? And this process works like this. So you have an eye here, and here you have an image plane. This is basically the image plane that is used to project this three-dimensional volume into, okay? So the way it works, basically, you cast rays across through the pixel on this image plane into the volume and sum up all the values that live inside. Basically, just like an X-ray would do, now you basically would do this, you know, on a computer. But you do a little more. You do also surface detection and surface shading, so you can see the structure of it, and you're going to composite those different structures together to create some sort of a composite pixel. So we'll see all this works. So this is the process of numerical integration along a ray. And if you want to go to another pixel, you just cast another ray at a different trajectory, and they're always straight. Okay. So sampling along the ray, so basically you will have to go and acquire sample points along this ray. Okay, and these in this case, they're just basically scalar values of densities, like some a little brighter, some a little less bright, depending on what that slice actually had or what that volume actually had at this particular point. Okay, and so you go from front to back, or you can also go back to front, doesn't matter really. From the bounding box entry to the bounding box exit, and you space these samples regularly along some sample distance. Usually use like half a voxel size, half a grid size, something like this, to make sure you don't miss anything. Okay, then you have to estimate these sample values, because remember this comes is an image, right? So it comes on a lattice, right? But these sample points may not fall exactly on a pixel. So you'll have to estimate those values from the surrounding pixel values in this grid. So let's see how this works. So essentially a three-dimensional pixel is what's called a voxel. Okay, this is a voxel here. And this is the eye again, and this is the image pixel here, and this is the viewing ray. And this viewing ray has stopped here in this cell. So each of these cells, basically, this is, if you think of it, that is a slice here, and that below is another slice, and these are the pixels in a slice, and they form a three-dimensional cell. And this is the sample that you obtain, and you got to figure out what that value is at this particular point, right? It's like a mix of these surrounding values that you know about. This is sort of something you actually don't know really, but you can estimate it from the surrounding values. Okay, so basically like this here. So it's just a function of, you have to measure this distance p along the x-axis. Essentially, if you think of this as being 1.0 apart, just like a fraction of 1, there's the distance q that's along the y-axis, a distance r that's on the z-axis, and this gets you to the sample point. Okay, so if these are the values that the voxels had, 1, 2, 3, 7, 6, 5, it's going to be like a mix of this, right? So you basically have to interpolate using these values what this value is. Okay, and this basically is done with this scary equation. Okay, so you basically, I don't want you, you can remember it, but you can just derive it, and I'll tell you how it's derived. I'll give you later on a little example how this looks. So essentially what you would do is you would try to estimate this value here between the value 1 and 2, between this voxel 1 and 2. You try to element. So basically you weigh this guy here times p, and this guy here times 1 minus p, and you'll find that here somewhere. Okay, and this basically gives you a value here. So basically it's just an interpolation of this and this. Then you do the same thing on this edge, same thing on this edge, same thing on this edge. So now you got 4 edges. Okay, then you're going to interpolate across here, You're going to interpolate across here, like here. You're going to interpolate because you want to be here. You're going to interpolate here, and you're going to interpolate something here on this other slice too, using those two values. Now you linearly interpolate between here and here, using the values you just got a value here, taking these, got the value here, and then you interpolate across. And that's basically how this works. Okay, so give you a little bit of an example. So like in bilinear case, just a single slice. Basically, this voxel here.
What can I do for you?
This voxel here has a weight, okay, and this voxel here has a weight, and this voxel here has a weight, and this voxel here has a weight, which is basically, 1 minus p, 1 minus q, and this and so on, right? These are basically these weights that I just showed you here, just in two-dimensional space. And this basically, by weighing these values here, using these weights that are derived by this distance times this distance, or really this distance times this distance, you get a weight that you weigh this gone by. Like that, the more, right? And so this basically gives you the weight. And then essentially, what comes out when you apply this equation, when you apply this bilinear interpolation, you're going to get something like this. So here, if I interpolate here, it's going to be really red because the voxel value here is red. If I go down here, it's really blue. If I go down here, it's really sort of magenta, and then here it's yellow. Right? You're going to sort of, and everywhere it's sort of smooth. That the orange comes here, and there's the bluish region. Looks kind of like a color map, but this is really what you get if you linear interpolate these different values. Bilinear interpolate these different values, it gets very smooth, right? And essentially that's what you're going to do in trilinear interpolation too, just now in 3D. Okay, so now you sort of understand how you can estimate a value for like when it's like on an arbitrary location in one of those cells. Okay, so now you're going to now let's take this value and map it to something you can actually see, like color. Okay, so first you also need to learn about transparency, opacity, because depending where you are in the cell, things are maybe visible or not visible. Things further down may not be as visible than things further up, depending on how much material has been between you at this particular point and the eye, right? That is basically occluding material. Okay, and we're gonna represent this as transparency and opacity. So basically the point really is there is one more channel. Like there's about red, green, blue, RGB, and now there's the A channel, opacity channel. Okay, which is, and opacity is really just when it's totally opaque, you cannot see anything, then the opacity is 1.0, and when it's totally not opaque or completely transparent, opacity is 0.0, right? And this basically goes from 0, 1. It's basically opacity is just 1 minus transparency. It's just the opposite. This is fully opaque, and out here it's fully transparent or not opaque at all, right? And this goes like on a linear scale. So this is the channel we need as well. Okay, so we need red, green, blue, and A. And then we multiply this opacity by this RGB to create this weighting effect, right? So if I multiply red by opacity of 1, it looks like really solid red. If I multiply by 0.9, it gets a little weaker. As I go through, it gets very, very, very faint. Okay, so this basically is basically a weight that I multiply the red value by, and it it basically reduces the weight, the red from that, right? So you get dampen the white. So things that are further back, you know, if the opacity is very high in the middle between it, right, then that red will be seen very, very faintly. It's kind of like fog, right? It's kind of like when you see a red car, but it's a lot of fog in between, right? The red car will look like this, okay? So now this, mathematically speaking, this is basically what it looks like, right? This is basically this equation that you would use. So you would have a front and a back part, right? The front part is what is closer to your eye, and the back part is a little further from the eye. Okay, and the front part, you have to multiply by the opacity that front particle has. Like if the front particle is very opaque, then you want to probably, its color will be seen better than it's very transparent. So this is the first part. And the second part here is the back part. This is behind the front. But that gets basically the same thing. You multiply it by its own alpha, or its own opacity, times 1 minus a front. Basically, when something that's in front of it is really opaque, then this is going to be a very small value, right? And if it's not opaque at all, it's going to be a really big value. Then you're going to mix them together. So let's put a particular example to this, okay? Let's think about these two surfaces here, right? There's a blue surface. There's a blue surface here and a red surface. And this blue surface is actually in front of this red surface, okay? And this has certain values, right? So it's like a strip and another strip in front of it, right? And so the transparent of this blue is 0.75, so it means it's very transparent. Therefore, because opacity is 1 minus transparency, the opacity is 0.25. So these are basically go together. And the red one has an opacity of 1.0 and alpha of 1.0, and the transparency 1 minus 1, it's 0, right? So now we're mixing these two together at this particular point. At this particular point, there's nothing red, so you just see the blue mixed with white. And here you're going to see the red pure, and here you're going to see the overlap region, which is computed basically by taking the red times the opacity of red, which is here, times 1 minus the alpha of the blue, which is 0.25. So it's 1 minus the, okay, which is 1 minus 0.25, which is 0.75. So the red times 0.75 because it's pretty transparent, and then plus blue plus the blue times 0.25. That's its own opacity, right? You have to this its own opacity, right? The color times its own opacity plus the color of the back times that opacity times 1 minus the opacity of the front. And then you basically get this sort of very faint looking, you know, blue, right? It's a little, the red is has a little bit of blue mixed in, but not much, right? Because the blue is so transparent, right? You don't really see much. But if you increase the transparency, the opacity of the blue, and reduce the transparency, you're gonna get see a little more of the blue, right? And if you make it even smaller transparency of the blue, they're gonna see even more, right? And here it's solid, right? So now it's completely occluding the red, right? So you can see this in this equation here, right? So it's like the color is more and more blue. Here it's a little bit red mixed in, a little more red mixed in, a lot more red mixed in, right? And then if the blue would be completely zero, that would only be red, right? So this is how this opacity blending works, right? Or this compositing, that's how it works, right? You basically take two things, two color samples, one is in front of the other, and blend them together using what the opacities or transparencies of these color samples were. And this is nothing but this, right? When you cast a ray with this kind of scheme, right? You'll have like, you know, here, this guy here has a certain color and this guy here has a certain color. Depending on what the opacities of two samples are, you're gonna get a mix of them, right? And then you basically can express the two of them by just a single sample. So you just keep going from the back to the front, and I have this little slide here for that shows this. So back to front rendering. So this is like a current sample here with a certain color and opacity. And let's say you somewhere in point where you trace a ray from the front, from the back to the front, you'll see this color here, I minus 1. Okay, and this is the color I, right? And this is the next sample, I prime. Okay, then Ci prime is essentially just this color here times this alpha here, you know, plus 1 minus this alpha here times the color that comes from the back. And that gives the new color. Okay, and that's basically how you do it, right? And then that new color, basically you're gonna use that for the next step, right? This becomes here again, and then you merge in the next one. You just keep going from back to front until you no longer have anything in front of you, and then you just call that a pixel, okay, and store that in a pixel. You can also do this from front to back. Really similar, just now you have this color first, and then you have to merge with this color here, you know. So now you take, you know, the color here that comes out of this, because now you're going from the eye to the rear. Before you went from the rear to the eye, now you're going from the eye to the rear. Essentially, what you do here is you try to take this color Zi minus 1 and add this color into that composite, okay, which is essentially this color here is just, you know, basically 1 minus I minus 1, which is this. What this color here is modified by this alpha in front of it, right? Because you keep a buffer now on this, right? You basically accumulate the alpha as you go from front to back, and whatever you discover here, you modify it by this alpha that is there so far. Okay, so the color here, the color that comes out here, is essentially just this color here plus this color here multiplied by whatever is, you know, what alpha is here, 1 minus alpha here. And then you have to keep an alpha buffer too. You have to accumulate the alphas too, because you need it, right? Because you have to keep track of the alphas that are in front of you as you march through the volume. So this is the difference between back to front rendering and front to back rendering. Okay, back to front, front to back. So transfer function. Okay, so now you have these, you know, I told you, you know, that there's color and you have to composite it together, you know, and then you know how to blend them together, and you know how to aggregate these colors and make a picture. But now, where do these colors and opacities actually come from, right? That is coming from what's called transfer function. This is basically a mapping that takes a density that you got from the image, right? That you interpolated. Remember the interpolation? That you interpolated only a scalar value, like a density value, from that density volume. And now you turn that into a color and opacity, like this RGBA tuple. So basically that's how it works, okay? So you'll have this transfer function. Essentially, what you see here is a histogram of densities, okay? So here's the 0 densities, here are the 255 densities, and these are the values that you sort of have that the volume has. And here's the color that you map to each density. So you know, this density gets mapped to green, the higher density gets mapped to blue, lower densities get mapped to red, okay? And as you go through, so basically when you have a interpolated sample, you go to this transfer function, you figure out what color it should have, and this is the opacity. Like when, you know, so basically here in this case, we're mapping these values here to low opacities, and the small values and the big values we're going to map to high opacities. Just look this up, then use it in this equation that I showed you, and you're going to get this kind of picture. Okay, so you'll see like the, you know, yellow and the blue is like has the high values, and here's red, that's a very low, it's like a hole almost, right, with the low value, and so on. So this is basically the kind of pictures you're going to get if you keep doing this sort of compositing, right? So rays go through, interpolate intensities get mapped into a transfer function, comes out with a color and opacity, use the color and opacity in this compositing equation that I just showed you, and then do this for all the pixels and all the ray steps. Keep doing this, right? And then you're going to get a picture like this. Okay? So hope that sort of made this kind of process clear, how this works. So let's talk a little bit about specifics. Okay, so number one is like, first the question is like, where do you actually look at, right? You have to sort of figure out, because you can look at from every angle at this particular volume, right? You'll have to like figure out like where exactly do you look at, and how do you trace your rays into the scene. Okay, so the way you do this basically is this: you put the object in this what's called the object or world space, which is made out of x, y, and z axes, and then you put the eye somewhere, and the eye basically has a camera in front of it. It's a pinhole camera model. Okay, you have the eye, and then you basically parameterize this image plane by two vectors, u and v. Okay, and the normal vector here is basically this normal vector here that's perpendicular to u and v, where the cross product of those two vectors that becomes the normal vector. So this is basically the center ray from the eye to the center of the image plane along, right? This is the normal vector that's formed by this. And all other vectors are a little off from the normal vector, from the direction. So an array is specified by the eye position, a screen pixel, right? You connect the eye with a screen pixel, and then the ray direction vector is simply computed by taking this pixel location, which is parameterized by this u and v, we're going to see in a second, minus the eye vector, now you get a three-dimensional vector. Divide this by the length of this vector, and this essentially gives you the ray along which you trace. Okay, and then a point P on a ray is given by I plus T times this ray vector, and T is a parametric variable where you can choose like T 1, 2, 3, 4, 5, 6, 7, 8, and so on, right? Because this is a unit vector. So every time you increase T by 1, you march the ray one step in front, right? One step ahead and ahead and ahead, right? And then you, every time at every ray that you stop, you're going to interpolate and get the intensity, look it up in the transfer function, and start compiling the image, right? So the rays, you find the rays simply by figuring out, because you need to traverse this image plane, right? You'll have to go to each point pixel, and it's really simple, right? You just have to compute a delta I and a delta j. That's the spacing along the u vector and the v vector on the image plane, just the spacing. Basically, just the width and the height of the image plane divided by the number of pixels minus 1 along this image plane. That'll give you like the delta I and delta j. So you can if you choose a smaller n, you're going to get smaller delta i's, right? If you choose a bigger n, then a coarser image, then you get bigger n delta i's, right? This just tells you like how much resolution you want to have in your image, okay? So that's how this goes. And then image order projection. Basically, all you do is really scan the image row by row, column by column, okay? And then this is this parametric equation I told you. This is the indexing for the pixel. You start here at origin, I times v times delta j. That's the v is the vector, and u is the other vector, right? You just keep figuring out where in the world space you are, and by using v and u, you're always gonna be on this image plane, right? Because the u and the v are defined on this image plane, and that'll give you like a location image pixel, and then you just go from 0 to ni, and from j to and from 0 to nj, right? They'll get from the bottom corner to the upper left, okay? And then this is called the image origin, and these uv n are the orthonormal image plane vectors, right? So basically, this is how you do this, right? This is, you put the eye somewhere in the scene, figure out where you want to trace the rays, keep tracing them with this equation here, like this T parametric equation, and then you basically generate the image like that. Okay, so that's essentially how this works, right? So there's different ways in which you can composite these pixels that you find, right? One of I showed you one of them where you just added them or composite them together, right? But you can also just add them, right? You can just take a pixel, interpolate densities along an array and just keep adding them together. And what that really comes down to is X-ray rendering, right? It's just like X-ray summed rendering, right? This is the most simple volume rendering you can find, okay? Then the second one is maximum intensity projection, where you also go through the volume, but along array you will only keep the value that has the largest value, right? That'll bring out like very high density regions, right? If you only keep the largest value of that along array, then you're gonna get like the most opaque structures or the most visible structures, usually things that have been perfused by some sort of contrast agent. In this case, like an aneurysm or something like this, you want to scan, or that this is like you can see here the carotid arteries, because they have been perfused by an opaque substance called iodine, and then that iodine will show up as a very high value because it's very dense. Okay, that's like how you can sort of bring out these very dense regions. An isosurface is another one where you look for the object surface and then stop. Okay, so that we're going to see this in a second. And then full volume rendering is where you stop at surfaces, but you keep going and kind of add them together. Okay, then you'll sort of see inside an object like this. Okay, so basically X-ray, maximum intensity projection, or MIP, or MIP, isosurface rendering, full volume rendering. These are the 4 different volume rendering, most basic volume rendering modes that are there. Okay, so practical invitation. This is how you would practically actually do this. Okay, so essentially, almost all volume renderers now, okay, you can do this on the CPU too, but they all sort of work like this. They work like this. So you would basically figure out, you put the volume in a box, okay, put that object in a box. Basically, it's already a 3-dimensional array with like, it's usually always a rectangular array, right? A 3-dimensional rectangular array. And that usually you have to find, if you think of it as a box, you'll find out where is the rays entering and where are the rays exiting. Okay, so you find this entry and exit points for each ray, which you can find by simple polygonal projection. And the depth buffer we talked about last time, right? You just have to figure out, how deep that is and how deep that is, and that is where you can find the front and the back faces of this cube for any arbitrary viewpoint. Then you store that, okay? You store that, and then you'll trace the rays between the entry and the exit point for each ray, okay? And this is the kind of program that you would use, right? So basically, you'll start off, you'll compute the position, the entry. This is like this particular point here. You compute the position of it. Then you compute the direction. Remember, I told you you subtract the eye, the camera, from the position on the image plane. That'll give you direction, and you of course normalize it, okay, because you want the normal direction to be unit. And then you'll just go from the front to the back. I is equal 0 to 200. Let's just think 200 is probably the other side of the volume, probably less, but that's the upper bound. And you'll go through, and you'll stop at each point, and interpolate the value. This is called text 3D. Essentially, what this means is we represent this 3-dimensional volume array as a texture. Okay, a 3-dimensional texture. It's just nothing but an array, a 3-dimensional array of values at regular spaced. Okay, and we call it a sampler data volume. Okay, and we interpolate. What this does really, it's just interpolating this sampler data volume, which is this texture. This is the volume data set at this position that you computed up here, right? This is the first one. This is the entry point. Then you get a value out of this and you map that to a scalar. Okay. Then you're gonna apply the transfer function. Now you're gonna take that scalar that you just assigned, and that's the interpolated value in the sampler transfer function. This transfer function I told you about, right? It's a 1-dimensional array, and you're gonna get 4 values out of it: red, green, blue, and alpha. Okay. And then you do compositing. Okay, like what I told you, right? It is the front to back equation you're gonna use. 1 minus the alpha you had so far times what you got just now, the color you got just now, plus that's the destination, right? That what you already had before, right? So this is the front to back equation that I told you about. Then you update the ray position. Okay, now you update with this. The DST basically is the new color opacity, right? RGBA. You know, you keep track, you apply the same, you know, basically this is the old color opacity that you had, then you composite it with what you just got from the transfer function, composite it together, right, and then you get the new updated current RGBA value, right, and then you're going to advance the array, and you're going to discover the next part, right. So basically advanced array, position plus direction times step size, you know, we can set it to something, usually 1 or 0.5. And then we test if it's outside the volume. We're going to figure out, is this outside the volume or not? If it's not outside the volume, I'm going to go back, update I by 1, and going to go, you know, interpolate, get the next position, and do this all over again, right? And then this is basically this is what the volume render looks like. There's nothing else to it. That's what it is. It's very simple, actually, if you think about it, right? So this is basically a front to back rendering, right? We start at the front and ended at the back. So is this better, right? Actually, it is better because you can do early ray termination, right? Because you can whenever a ray is opaque, right? Because remember you accumulate the opacity, right? And the opacity keeps growing, and if there's more and more opaque structures that you discover along the ray, then its opacity is going to end up to be 1.0. If it is accumulated opacity is going to be close to 1.0. Usually you stop at 0.9. Then you can stop the ray, right? You can just terminate the ray and start a new one, right? Which saves a lot of time, right? You don't have to go to the back. If you do back to front rendering, you can't do that because, you know, you always have to see everything, right? Because you can't stop it because you have not discovered what's in front of you because you're just discovering that. So front to back render is much better. And also allows you to do empty space skipping. You can basically mark some cells that don't have anything in there. You can just skip over them, okay, and then just don't look at them. I don't even interpolate them. Okay, that's another trick how you can accelerate volume rendering. So early ray termination and early empty space skipping. Just skip over stuff that doesn't have anything interesting. You know, then you just that can be two pretty good methods to accelerate volume rendering. So the one thing is the isosurface rendering. Sometimes you really just want to see if there is a surface or not, right? Remember, in graphics objects, your surface is given to you as a mesh of polygons or a description, a boundary description. But in volume rendering, there could be any surface, right? There's any surface is possible, and you have to define which other surfaces are that you want to look for. You know, for example, for a smooth sphere, you'll see like this has different values, right? The interior of the sphere has a higher value than the exterior of the sphere, and by choosing the ISO value to a certain value, you can basically make the sphere look bigger or smaller. Okay, if you choose an ISO value of 50, it looks like this. If you choose an ISO value of 200, it looks like this, right? So it's like the outside is a little has smaller values than the inside. So this is basically the basics of ISO value rendering. And then once you have discovered the surface, you stop the ray, right? You got just look at the surface. So interactively create geometry on the fly, basically. That's what you're doing there. Okay, it's called the ISO threshold. And then you can sort of look at things like this. So if you set, for example, if you have a data set with a foot, a volumetric data set of a foot, then if you set the ISO value to 30, then what's going to happen is there's going to be a lot of like noise and air in there, right? Like things that when you acquire the CT scan were like set to values that are not really object values. They're just sort of, you know, values that are not zero. But if you set the value to 80, which is a little higher, you know, the noise is usually low density. ISO value 80, something like that, you can get like a really good surface description of this foot. If you set the ISO value to 200, which is much higher, you know, usually what happens when you have a higher value, the boxes with higher values are usually like the bone usually has much higher values than the skin. So if you set the ISO value to 200, you're gonna go right through these. Your ray will go right through this skin and the muscle and go only stop at the bone, right? So it's just like this. But you pass a ray through, you interpolate a value, say, okay, my value is not 200 yet. I'm gonna go ignore you. I'm gonna move on until you finally find one that's 200. Okay, just by ray tracing, right? When you cast the ray, you decide interpolated, is the interpolated value lower or smaller or greater than the ISO value? If it's smaller, I'm going to take the next sample point. If not, I'm going to do isosurface rendering, okay, like this. So isosurface rendering detail, right? So here's the ray. This is your voxel grid, okay? And these are the voxels here. The white ones are that voxel that have a smaller value than the ISO threshold, and the brown, gray, the darker ones are the voxels that have values of the equal to ISO threshold. And you only want to see those ones, right? You don't want to see these brighter ones because they're they could be the skin, but you want to see the bone. So basically, what you will do is you cast the ray across until you interpolate something that has this ISO value that you have set. Then you stop there, okay? Now you stop there. But now, remember what I told you about illumination and shading last time in class? You'll have to determine a normal vector, right? The normal vector, remember, normal vectors are really, really important to find out about the specular and diffuse shading, because diffuse shading and specular shading will bring out the shape, right? If you don't have that, if you don't use diffuse and specular shading, or at least diffuse shading, you don't really see these kind of pictures, right? You don't really see the real shape of a foot. All you will see is like, if there's a foot or not, but you don't see the shape of it. So in volume rendering, you have to estimate the normal from scratch, because you don't really know it, right? Because you just discovered the surface, you don't know the normal at that surface, right? So now you have to estimate it, you have to basically estimate it. So all you do is like apply this what's called central differencing. You basically figure out the gradient along this direction, and the gradient along this direction, and then also along the z direction, which I don't show. And all you really do is interpolate a value here, in behind your sample point, and one in front of you, and subtract the two. Interpolate one above and below, and subtract the two. And then what they'll give you basically is a vector, right? It'll give a vector. So if this guy is higher than this guy, then a vector will point up here. And if this guy is higher, this guy is lower than this guy, a vector will point like this. So these two vectors then will be a normal vector. So these are basically here the normal vectors. This is what you would get, right, from doing the central differencing. Like this obviously is going to be lower than this value here, so the vector will point in this direction. And these values here are going to be the same, so there's not going to be any deviation. So the normal vector will actually point in this direction. And then you can apply shading. So I have this here, right? Once you have the normal vector, and you have a light source and an I vector, then you can compute this H vector, remember what we talked about, and then you can actually compute how much light gets reflected towards the eye from this particular surface that you found, right? And then this is kind of all you would get. Okay, just the same standard shading equation as you learned last lecture, you're going to use here as well. The only difference is really have to figure out where your normal vector actually is by reconstructing the normal vector using this central differencing method, where you just take the front and the back, top and the bottom, and left and right, and subtract each of them, figure out the remaining vectors, put the vectors together into a vector sum, and then this will be a normal vector. You have to normalize that normal vector, and then that's basically what you will use for shading. Okay, that's basically what you will do. So far, hopefully this is clear how you do this. So now comes full volume rendering. Full rendering is basically the case where you don't stop at the isosurface, but the case where you stop at a surface, you do some shading, but you don't stop if your alpha is not yet close to 1.0. Then you just march on. Basically, what this will give you is structures that are somewhat transparent, right? You'll see you see the brain inside the skull. You can see the skull a little bit, but then the brain you can see as well. Okay, something like this, right? This is like some good sort of these full volume rendering results, right? You can see the surface of the hand, but also the bone, right, at the same time. Because this looks, and you can see the vessels shining through. This is a really nice volume rendering of a hand. Okay, where you basically found structures that had some gradients in them, right? Because you needed that to find the isosurface, where the normal vector was not 0, right? There was a little bit of a magnitude to it. Then you did shading on it and you marched on. So that's basically what you did. Here's another equation, right? So what really this comes down to, and this sort of leads me to the last part of this lecture, volume rendering really is a classification task. That's where it sort of goes a little bit into the machine learning and data mining and area, right? So basically you need to define on the fly which parts are transparent and which parts have color based on the value that you interpolate. Okay, so you have to classify that, right? So basically you interpolate a value and you apply this transfer function and figure out how much light gets absorbed and how much light gets emitted. Okay, so essentially this is the color the object has and how much material from the back can shine through. Okay, this is essentially a transfer function. So classification is essentially, when you look at it from this perspective, just as a classification task, you'll see like this, right? So this is like, and here you segmented out the surface, here you segmented out the vessels, right? You just chose a different transfer function, right? And you saw all of a sudden, here you didn't see it very well. Here you removed all the brain and just looked at the vessels, and here you shaded them, in different ways, right? You can see a little more, right? So these are all classification tasks, right? First, you have to determine, am I seeing this voxel? Do I want to see it or not? And then, how do I want to see it? What color I want to see it, right? So this basically is a classification. And this stuff goes in real time because users want to change that in real time. Users want to quickly see where, want to explore the volume and do this in real time. Okay. And essentially this is what it comes down to, right? This is the transfer function again that I showed you about before. Now this is what's this sort of horizon in the back here. What this really is, it's essentially, is in the back there is the density histogram. So this tells you how many voxels had small densities, how many voxels had large densities. Okay, and you'll see a little bit, there's a lot of voxels here that probably air, some voxels here, and then there's a hump, and then there's some more stuff here, and there's a little bit here. And then by assigning these density intervals a different color, you can identify those densities in the rendering. So this is just a slice, right? So you can see here, here these are these high densities, and then here these red ones are mid densities, and these white ones are the low densities. So that turns out that white matter has a little higher density than a gray matter, for example. Yeah, that's interesting to know, right? And here this is probably water, that has very high density. So that's basically, classification, on-the-fly classification, using the transfer function, assigning color to different regions, and then using those colors and coloring the slices. So now, when you look at it like this, so I want to teach you a little bit about how to read these transfer functions. This is a different transfer function than the ones I showed you here, right? This is just a transfer function, how many the histogram essentially. This is a transfer function that's made out of the scalar densities and the gradients you find for each density. So essentially what this really shows you is each point here is essentially a voxel or a pixel, a three-dimensional pixel that had a certain density and when you look here, had a certain gradient, right? So basically the gradient, right? Not just the magnitude gradient. Basically just compute the difference here, difference here, difference here, and you find the magnitude of that, and basically it tells you like how strong that voxel was. So if a voxel has a very high gradient, then that just means that voxel was on a surface. Because every surface has high gradients, right? Every surface has big normal vectors because there's going to be a big transition from lower values to higher values, right? For like air and skin, or skin and muscle and bone, right? Things like this. There's going to be a transition from certain density values, right? There's like vastly different density values in skin as opposed to air, okay? And that just basically tells you whenever you're here, then you know, aha, this density here, you know, must have a surface in it. Same thing here. This density here must have a surface in it. This density here must have a surface in it, right? So you know that, right? Because essentially what you really want to show to the user is surfaces, right? You want to reconstruct the geometry of the volumetric data set, right? You want to like see the surfaces, because the surfaces are what you're really interested in. You don't care if there's like, you know, a lot of air or water, you know, and how the water looks like. You want to see the surface of the water. You want to see the surface of the skull. You want to see the surface of the tumor, right? You want to see these things. So essentially, this is work by Gordon Kindleman, long published ago. And basically what it basically says, gradient magnitude, if you look at this particular slice here, if you just zoom in this particular region, you'll see like this edge here, this is just a gradient magnitude. You can see the gradient magnitude is really high at the surfaces, not very high in the middle, in the interior, and then it gets high again when there's a new structure inside, right? So basically here you see this high gradient at the surface of the foot. And as you march across this, you know, you'll these are all here, this red thing here, right? This blue dotted line. These are basically the densities you're gonna get, right? Low density, higher density, even higher density. Because this is in the foot, right? This is just the edges shown. But the foot gets much denser, right? Here you can see the foot on the right hand side. You see dark, low density, gray, the higher density. In the middle, it sort of transitions from low to high, right? From low to high. And this here, right? This line here is essentially nothing but along here. And this shows the gradient that you measured along each of these sample points. And it turns out whenever you hit just the transition from a low density area to a high density area, which is the surface, you're going to have a high gradient, okay? So all you really need to find is basically the boundaries. All you need to really find is these arches, right? So you have to find these arches. You know, find out where are these arches. Whenever there is an arch in this two-dimensional scatter plot, which is density over gradient, then there must be a surface. See, there's one arch here, there's another arch here, there's another arch here. So basically there are three surfaces, okay? And you just find them like this, right? So essentially, and this gives way to what's called multi-dimensional data transfer functions, or, you know, two-dimensional transfer function, if you will, right? So basically you find out if this is like a typical fx is this density field, then this is the gradient as it gets high when you just at the surface and then low again, and this is the second derivative. So you really have to find the zero crossing of the second derivative to find out where precisely the surface is. And this is what this work does, right? It finds this, it goes into this thing, figures out where these arches are, which is basically where the second derivative goes to zero, and labels those as surface and gives them a high opacity and nothing else. You have, for having a high opacity, you must be here, okay? And then you get the color only here, okay? And basically this is what comes out of this, right? This is called the dual domain interaction paradigm, which is quite old, like almost 20 years ago. But it's really, really effective way to really show volumes, you know, in a very high detail that you couldn't do really if you didn't do this two-dimensional like density over gradient analysis. You could never get these surfaces the way they are, right? You would sort of find them a little bit, but, you know, not quite like precise like this, right? So essentially, okay. So I'll show you like a video where this is shown. Okay, here's this video for the data set, which is called the engine data set, okay? So let's go here, right? You go in here, and then you basically do the surface, right? You take this window, you take this window here, which is really, it's just a piece of the, you can put this window everywhere you like, you can move it in 3D, okay? And you measure, within this window, you measure the densities, okay? Then you take this crosshair, okay, this crosshair. Oh, sorry. Where's the crosshair? Now you take the crosshair, and the crosshair, basically what this crosshair is, it is just, you go in this point here and you just figure out the density values within a small cube around it, okay, with small cube around it, find the 8 density values and plot them here, right? Just plot the density values here, like these voxels basically. These voxels that are in this cube around this crosshair, show them in this plot. Show them in this plot. And you'll see, like, as it jumps around, as you move it, it jumps around. And whenever it jumps around, it makes this sort of, traces out this arc, right? It traces out this, this. And whenever this arc is shown, right, whenever you're on the top of this arc, remember what I showed you before, whenever you're on top of this arc, you're very likely to have a surface. And then what this interface does, it places a color there and an opacity, right? So it makes these little widgets here, makes that green or red. You know, how you can sort of make colors around it. You can really now label the surface with particular color and make it opaque. And sort of iteratively go through this and one by one mark those surfaces and get a really, really amazing three-dimensional object out of that, right? Which is actually a very complicated object to really find like this. Like every little detail you find there, right? It's just the density field, right? With overlapping density ranges, but you can find them. So it's a little bit older, that's why it's a little bit slower, because it uses an older GPU, right? But and a little grainy, but you know, because it's from 2001. But the concept is really the same, right? Look how nicely this looks, right? You can just see the surfaces and they're a little bit transparent, right? And it's like a painting, right? Same thing you can do with this skull data set, this head data set. Similar concept. Try to find these arcs. Whenever the arc is at the peak, this must be a surface. Place the color widget, opacity widget there, and then label that with a different color, right? And then apply that everywhere, right? Because once you found this, there's going to be, it'll figure out all the voxels around that surface that have similar profile, right? So basically, by marking this, you'll essentially find all the voxels that are part of the surface, not just the ones you just found with this window, right? Because you're marking all of them, right? You just found an example for it, and then mark all of them. It's not that convincing, I think, but the engine that this is really good. So, transfer function clinical practice. Okay, so, you know, you cannot imagine a doctor using this kind of interface to find surfaces for a patient, right? The laborious kind of activity, right? They go around and place these widgets everywhere, and then, you know, it would be very expensive for a doctor to do that. A doctor would take, even a lab assistant, right, wouldn't want to do this. So people really wanted to find an automated method that doesn't require you to elaborate, to do this kind of thing. So Christoph Resk-Salama in 2006 already found a machine learning approach how to do this, okay? So essentially, it uses all the tools you already know from previous lectures and applies it to volume rendering. That's why I like this volume rendering, because it really shows this application, because it really shows you how data mining and machine learning can also be used for volume visualization, okay? So basically, what doctors want, right? Doctors always want a slider. Basically, you want to, let's say a doctor has a patient and he put him through the CT scanner or MRI scanner and wants to see like what the head blood vessels look like, if there's an aneurysm or anything like this, right? So he wants to use volume rendering for that, right? But every patient is a little different, so it's very hard to really apply a standard transfer function to it. So you have to always do a little bit of changes to the transfer function until you really get what you want to see. And of course, doctors don't want to do this, right? So what they want really just is a slider. Just want to slide from left to right, and somewhere along this slider position, you'll get the right structure that you're looking for, right? Sometimes it's a little small, and here it's a little too large, and here it's just right in the middle, or a little bit to the left. Basically, it's just here's a little too noisy. Here you don't really see everything on the left. You know, somewhere in the middle, you don't know where it is, but somewhere in the middle, it's good, right? That's about the kind of work a doctor would do, right? Not more than that. The one-dimensional transfer function, that's all they want, a slider. So Resk-Salama, he developed a method in which that allows you to design this slider, okay? So what he did basically, it's a machine learning approach, essentially a machine learning approach. He acquired, like, let's say, you know, I don't know how many, 50 data sets or something. For each data set, he had, you know, lab technicians or experts design transfer functions, okay? The kind of transfer function like this, remember, with these arcs, right? These sort of widgets here. Design these widgets. So put a widget like this on these curves, right? And parameterize this widget, right? So you say, okay, all of them look like triangles. This point is here, this point is here, this point is here, interior like this here. Just basically 1, 2, 3, 4, 5, like 4 and 3, 7, right? So 7 points. Oh, I think I had more. 1, 2, 3, 4, 8 points. Okay, 8 points, right? Parameterize this by 8 points, and essentially these 8 points are 16 values, like one in the scalar dimension and one in the gradient dimension. Okay, so you have 16 values, a 16-dimensional data set. And for each data set they looked at, they would find the optimal transfer function like this, right? The optimal way to catch this aneurysm, okay, or whatever, or this blood vessel, right? The optimal way how you can get this surface pretty well. And they took like 50 of them and found the perfect orientation of this triangle here, right? And these positions of these points, and then collected it and made it. They can also find different kinds of shape, but let's just look at this one. So 16-dimensional function, okay. And then what they did was they went and now you have a 16D function, and they did a PCA on it, right? The principal component analysis, and found out basically the major PCA axis. This is the major PCA axis, right? These are the two. You know, this is basically the data. This is the major, and this is basically the major PCA axis, right? And this is the second major. Project everything onto the major PCA axis. So now basically you have a one-dimensional distribution, right? One which is arbitrarily oriented in the real feature space of the transfer function, right? Arbitrarily oriented, but now you have a real axis like this, and now you can just go whenever you have a new volume, right? A new volume. Then you'll just, you know, it'll probably be one of those, or like maybe somewhere else a little bit, but definitely somewhere it'll be, and any new volume that you acquire will require one of those transfer functions or something in between, because you hope that you sample the space of transfer functions sufficiently dense enough, and then all you really have to do is go left to right and see which one fits the best. Just go left and right. So each, as you move the slider from left, from low here, from up here, you'll find one of those parameterizations that fit you well. And because each point is actually a parameterization, you can reconstruct that parameterization to map that point back in high-dimensional space, right? And then you find the parameterization, find the right shape of this, and then you can just look around and see, okay, well, this one this one was good, you know, this one was good. So it's a really nice way to use high-dimensional data analysis, dimension reduction with PCA, reconstruct this one-dimensional function where the variation is the highest and most promising, and identify good configurations from that, bring back the configuration, and render the volume using this, right? So this is essentially what this comes down to. So, okay, so hopefully this part here taught you enough insight about volume rendering, and then what you can do with transfer functions and how it all works together, and what you do for your lab, which is from Salt Lake, from University of Utah. So you can download it. I give you a lab file that will tell you how to do it. So here's this program here, okay, ImageWiz 3D. But basically, when you call it, which I just did. You open a data set, and there's a few data sets. I only have this one, the engine data set. You open it, okay, open the data set. Then what you get basically is this transfer function window here and the viewing window, right? You can rotate it, you know, so it's pretty good. You don't even need a GPU for that. It's really, really fast. You can just use a regular, this computer has a GPU, but not a really good one, right? And so, you know, actually it's a laptop that I have here. And you can just rotate it, right? So you can see the isosurface, right? And here's the transfer function I talked about, right? So let's, you know, there's also other things you can do. You can do 2D transfer function editor that uses this paradigm I showed you, that the scalar versus gradient space isosurface setting you can do. But for the lab, I only want you to use the 1D transfer function editor. I really want you to get a feel. Oh, what happened now? It went away, so bring it back. Okay, so I really want to get a feel for this, right? So let me tell you a little bit about the sequence of this. So basically here you have the red, green, blue alpha channel. So let's first select the alpha channel first. So okay, this curve, this is the histogram. You know, you can see there's a lot of air there. Here's something there and something else here, right? Who knows what it is? If you take the alpha transfer function all the way out here, then basically, you know, let's bring all the colors down. Okay, let's do that later. Okay, then, you know, you'll basically see not much, right? So now, if you tune this alpha transfer function, of course you have to take that off, right? Take it off, take all this down. You can see something, right? This is a different color now, you know, so I can bring back the I don't know what I took away. Oh, what did I do? Always have to turn off this, right? So, you know, the green. And red. So now everything is gray again, right? So now what you're going to do is, let's look a little bit what's inside this, right? So now you can take the alpha down like this, okay? So now I'm only looking at these structures that are inside, basically the high density structures, you know. As I go out more, I lower the alpha, right? I'm gonna basically bring back the lower intensity regions like this, right? This is the low intensity region like this. And as I move the alpha back out, I'm basically ask the rays, okay, please ignore everything that has low densities and only show me high densities. So now what you can do is you can say, okay, I want to make this red, only red, right? So I'm going to take the green. Always turn this off. Only use the one that you don't. Take the green out. Okay, green. Remove the green channel completely. You can also keep it purple if you like, but let's also take the blue out. You know, take the blue out too. Now the blue is out. So now it's only red, right? Only red has remained. Okay. And now you can say, okay, that's great, but I want to see how this looks like, you know, with the engine body too, right? This is with the gears, but I also want to see the overall shape of the engine. So okay, so let's bring that back in. Okay, let's bring that back in. Let's take this off and just bring alpha back in. Okay, so I'm gonna do like this. I'm gonna make a small hump here. So now I have a little bit the outside surface of this engine, semi-transparently, because now I don't bring, see, if I make this very high like this, I'm gonna completely make it fully opaque, and I don't see the interior anymore. But if I bring it down like this, draw it like this, you know, then I gotta only see the surface, then I only make it a little bit transparent. And now, of course, this is red on red, and of course this, you know, maybe you want to give it a different color, maybe green. So I color this green. Okay, take the green channel here, make it green. Of course now it's red and green, right? Because the red is out. I can take the red out. It looks pretty cool actually. But if I want to make it just, you know, it's yellow, and because now it's red and green mixed, right? I can take the red out. I can take the red out. Now it's green, right? Red and green, right? I can make the blue back in, right? Wonder what that looks like. Okay. It looks like this, green, and now it looks sort of like a mix of blue and green. Okay, so so this is basically how you can paint. How you can nicely paint. It's really nice, right? You can really see it. You can play a little more with it. You can play a little more with it. Now you see a little more surface, right? The red is a little bit disappearing, right? So it may not be that good, right? I have to make it a little more transparent. Now the red shines more through, right? So anyway, so basically what I want you to do for the lab, I want you to create these kind of structures, right? So an full isosurface where it's just the surface only, or like where something's shining through, but the outside surface is really nicely defined, something like this. So there's other data sets that come with it. There's a head data set, and I think a lobster, I think, they come with the distribution. So try to also look at that. Okay, so this is basically how it looks like. For lab 3, basically I want you to download this ImageWiz 3D from this website here, which when you click on it, you'll see it. Download the datasets from that website. And don't use the transfer functions files, okay? Make your own transfer functions, okay? Don't cheat, okay? Then render 4 isosurface images, and you get 10 points for each. So basically take 2 different datasets and use 2 isosurfaces for each and render them, okay? Only the isosurface, not mixed, right? And then render 2 images with multiple isosurfaces showing, like the one I showed you for the engine, right? Where you had the outside and the interior or something else, whatever you like. Make it like interesting looking, right? Pick from 2 different data sets. So, like one composite image for one data set and another composite image for another data set. And then you get 10 points for each. And then, if you make, if they're looking really good, then you get 2 extra points. Actually, I only give 8 points for each, and then I give you 2 extra points if they look good, right? I'll change that to 8 points. So let me give you some special instructions, okay? So number 1, I want you to only use the 1D transfer function editor in that workspace, right? So please don't use the isosurface settings, okay? It's kind of a cheating, right? So I really want you to experience how this 1D transfer function editor really works. Get a feel for how you take densities and map them to visuals, right? You can experiment with the lighting. You can compute. There's the lighting. You can change the lighting here, right? You can move the lighting, right? You can create interesting effects, right? You can also change the intensity of the lighting, make it more. You can change the diffuse and the highlight color, right? So it's like this without highlighting here, this with highlighting, right? So you can do lots of interesting things with that. So you can experiment with that for sure, right? And get, you may get nicer volumes, nicer renderings like that, right? Like this is highlight, right? Here you should see a highlight. Here's the highlight, right? Here's the highlight, right? But then take it off, no highlight. Take it on, highlight, right? So there's no highlight here. Probably. Here we go. See the highlight here? There's the highlight here. Take it out, the highlight is gone, right? Highlight is right here. So, intensity too. Yeah, you can change. So you're very welcome to experiment with this. That's not the right file. That's the file. So you're very welcome to experiment with the lighting editor, okay, which is right here. Just enable it by selecting lighting. And then what I want you to deliver, basically, capture the entire window, okay? Capture this whole thing, like this one. Capture the whole thing, okay? You don't have to have this in there, but I really want to see the picture and the transfer function at the same time. I really want to see both, right? To really show you, and then pick a nice viewpoint, right? Just really get all of that in a single picture. So you can really show me how did you make that, okay? And right, and then there's no image save features, I think. So just have to grab the picture somehow, like with OpenView or something else. Okay, there's no image save feature. It says there's recording, but I don't think it works. And then submit some RAR or archive file and put it on Blackboard. And the deadline is Thursday, March 26th. Okay, so that's basically that's the lab, right? So okay, so this basically concludes this lecture. If you have any questions about this, then feel free to post message on OpenView on Piazza, not off Piazza. Okay.